Center for Robotics Research, Department of Informatics. Um, so this is a talk I gave recently at King's College to an audience, a diverse audience ranging from who studies to humanities and robotics. So the topic is are humans autonomous and are autonomous machines dangerous? So I particularly try to address this topic because a lot of people in the society are concerned about this rise of robots and their intelligence, and where are we leading, and is there a thing called singularity, and whether it is coming, whether it is real, things like that. So I'm not pretending to be an expert who knows everything, but this is some of my personal thoughts. Um, so these industrial robots in 1980s made wonders in factories and revolutionized the factories. And then they were just fully programmed, and then they did whatever they were programmed to do, very fast, very efficient. Um, but now there's a project we are involved in at King's College London. Robots can adapt to changing environments. So this is like somebody could move the object and still the robot could think and then readapt without having to reprogram the robot. So the one on the right, these robots cannot deal with that kind of changing environments. Like if the environment changes, the whole program fails. So this is a big feat from 1980s robots to now. This is 2015, and this is what we can do. And then even this kind of cooperative behaviors can be done. Like so, if one robot finds that the object has been moved, the other robot finds that I can help the other robot. So it is they can coordinate and help each other. So this was a big European Union funded project done in collaboration with IIT, Italian Institute of Technology, King's College London, Profactor, Fourth, and CVUT. Uh, so this is very much industry. And then there are other types of robots that can go in outdoors and then go to the like unstructured environments. And then this robot is, I guess, is the Australian robot that can transport material in a construction site or in a very remote environment without let's say roads with marking. So these robots look very intelligent, but if you look carefully, this kind of movements can be programmed using some kind of a stacking of simple motor programs. For example, if you take, let's say, the robot wants to go from here to here, you can have a attracting force field. A force field is something where if you know the position of the robot, the function spits out a force vector, right? So that is any position, given any position, the program spits out the force vector. So basically it knows how to attract the robot from any position to the target point. So you run this program on the background, and then you run another program which is a little different. This force field is something that swirls around an obstacle, and then where you know the position, it has a force vector, but it is not trying to push the robot from any position to a target position. It tries to push the robot round and round a obstacle. So what happens if you run these two programs together? So it leads to a virtual summation of these two force vector fields, and then it creates some kind of a force field that looks like this, and that can get a robot from start to the end in a seemingly intelligent way that looks like, okay, the robot has intelligence to avoid the obstacle but still reach to the target. But what really happens is, like, so these bits and bits of programs running in parallel, so we call it concurrent processing, concurrent running of programs that look at different environmental cues. For example, this program looks at the target goal. It doesn't worry about the obstacle. This program looks at the obstacle, and then this is connected to some kind of sensors that look at the obstacle. This is connected to some other kind of sensors. So when they run in parallel, it gives rise to this kind of behaviors. So intelligent behavior does not need necessarily have to be programmed as it looks like. So it can emerge from very primitive programs that run in parallel. So the whole hypothesis, like, so even human intelligence can be working like this. We don't know. So it is without a central regulator. So if you look at this kind of more like defense kind of robots, they exhibit very intelligent, very dexterous behaviors. For example, this Boston Dynamics robot. So these videos were shared by my colleagues at Carnegie Mellon University Robotics Research. And this robot is from Boston Dynamics. See what happens. Right? So when this robot goes in the right, so it can roll down and passively, and it doesn't need to use a program to roll down. The body design itself is, like, for example, this robot is designed to be very symmetric across a horizontal axis, so that, like, it can land on its belly down is fine, like, it just can get on with the task. So this big dog, it can roll down some kind of a slope if it kind of falls, and then the program doesn't have to necessarily take care of all the movements. There's kind of the body doing some kind of program, body doing some kind of computation. So this is another advanced concept where we don't limit the computation to the processes for explicit coding or mathematics. By nature of the body design, we can do a lot of computation in the morphology of the body. We call it morphological computation. So the body doing computation. So a classic set of examples is this. This is Andy Ruiner's passive dynamic walker at Cornell University. So this robot can walk down a ramp without any kind of a single processor, without a single code, single sensor. So no sensors, no processors, it can walk, because just the body is designed so that the gravity is enough to just drive it like a human. So this is a dead fish. This is some work done at Harvard University first, and then what they did was they just put a dead fish in the water in a tank, and then started a water stream against the body of the fish, and then at some speed they gradually increased the speed of the water, and then at some speed the dead body kind of swims forward, and it looks like a live fish. So what is going on here? The brain is not doing any computation here, but the body body and the environment together does the computation. So it is kind of weird in the sense that the body and the environment seem to have some complementary components of a program that when put together, or when the conditions are right, this program starts to run out of nowhere. It is not in the body alone, it is not in the environment or the water or the turbulence alone, but when they are put together, this program closes the loop as if there's a code that starts to run. That is so exciting for me. And then that program can make a productive thing or a propulsion force that makes the body move forward just like a live fish. So if this program is there in live fishes also, it must be, meaning the brain doesn't have to do a lot of work. The body and the environment is running a passive program, and then the brain may be doing just stiffness control of the body, and then just tiny little tuning of the body, so that the program can run more efficiently. So this is amazing. This is the thing about morphological computation. So a recent experience I had in my lab. So we were working with two crafts people, and then they made this nice little craft out of paper. And then the cool thing about this is like you could rotate it around, but when you hold this bit, the bottom bit, in one hand, and then you can hold the top bit on the other hand, and then you can rotate it around. You don't see it's anything complex. It is so simple. And then they asked us to see if one of our robots could rotate it, and we thought it's a piece of cake. And then we just started to program just a circle and then get the robot to move it around, and we couldn't do it. And then the program, the robot started to damage the thing. It couldn't do as if just like we did using hands. Then we just thought for a while, and we just put a spring in between the robot and the tip of this exhibit, the artifact, and amazingly, it did the job. So, meaning we can have a simple program running in the robot. It is just like going round and round on a square, and then the spring takes care of energy exchanges between the object and the robot, and then you can see at the corners there's a lot of peak forces, like kind of singularity forces, that the program doesn't have to negotiate, and the program just allows spring to take care of those things, like absorbing this energy the forces, and then release that work, release that energy when it is not needed. So this is a morphology, the body or the spring doing the computation and doing the simplification for the robots program. So this is another example for morphological computation. So future robots are not separated from the environment. The future direction, our direction is how to get robots to be kind of embedded in the environment most efficiently through efficient bodily mechanisms. This is another word is embodied intelligence, and then the body doing passive computation to simplify the task for the brain, so that you can have very simple brains in the robots that does marvelous things. And then in kind of summary, so you can put these things together, and then you can say, okay, so there's an environment, and that environment poses opportunities and threats to the robot, and then the environment can have pieces of programs waiting for the body to catch. And then if the body is tuned to the environment, it can run programs on its own. And then if you have a control system, it can also mediate this body environment kind of communication. Right? So this we call computation as a holistic way of looking at it. So okay. So what is an autonomous machine then? So if the body and the environment can do things on their own, and the program is doing some kind of mediation only, who has control over things? And maybe the body and the environment doing the whole computation, as in passive dynamic worker, who has control over things? So there's no definition for autonomy, but my kind of working definition is a machine is autonomous if it has the computational resources to map a situation to an action without any outside interference. So when I say action, action can be change of control parameters, changing a section of its own code, uh, changing the sensors themselves, and change the morphology of the body, camouflage, control actuators like motors, and a whole repertoire of things it can do. So, and then maybe autonomy is about like maybe taking no action at all. So this is just deciding to give up. So that is also autonomy. So this is not a perfect definition, but it's kind of good enough for most of the cases. So a semi-autonomous machine is like a machine um, that allows real-time interference from a human agent in the process of taking action. So now I'm going to scare you a little bit. So this is a landmine. So in a landmine, what happens is like in the most primitive shape of case of a landmine. So somebody steps on it, and then there's a knob, a spring-loaded knob, and then there's a pin um, mounted in that knob, and then the knob goes down, and then the pin scratches some enriched explosives. So then what happens is the the this explosive explodes, and then the whole thing explodes, and then that is it. So the thing is, there is a pure mechanical program running here, and then that can take action, that is detonation, upon an environmental stimuli. So there's a stimulus is the pressure. So somebody stepping on it, and then it does not care about what is giving the pressure. It can be a human, it can be an animal, it can be just a stone, it can be a coconut falling on it, or anything. The force, the enough pressure is what is needed. So and then the program autonomously completes it, right? Automatically completes it. So there's a slight difference between automation and autonomy, but for me, this is autonomous system. It it maps a situation to an action without any interference. A full freedom. It has a full freedom to map that without asking anybody. So if it is difficult to understand that this is a program, so the exact equivalent can be written like this: if pressure is greater than a set threshold, then start detonation process. So if you run a piece of code like that, so you call it an autonomous program, right? And then why can't you call this autonomous program? So this also a program on the right hand side. But don't be misled that a autonomous system always has to take a visible action. So this is the most primitive example I can take. But it can, as I said, it can be this or landmine is it can change the stiffness of this spring, or it can change some kind of a parameter of this explosives, or it can take do nothing. So the autonomy can be hugely wide, but this is also an autonomy. So we don't appreciate that this kind of autonomous weapons are already in 61 countries on this planet, waiting for something to trigger it. And it can often be people, these elephants and this child stepped on the horse. So in Sri Lanka, this video clip was shared by courtesy Humpty Dumpty Institute, a New York-based NGO working in Sri Lanka, Jaffna, removing landmines. So see how difficult it is to do manual demining. This is the 21st century state of the art of landmine detection and removal. We have technology to go to moon, land a robot on planet Mars, but we don't have technology, unfortunately, to look for landmines on our own planet. So this is some brilliant person in Afghanistan who developed a passive dynamic walker to look for landmines. Like so, what they do is like so just put some sticks, and then there's a bow that rolls in the wind, and then if it steps on the landmine, it explodes. And then if you throw in a bunch of that kind of rollers in their deserts, so that might do a fair job before somebody steps on those things. So that is autonomy and counter-autonomy of detecting autonomous weapons and landmines. So that the autonomy can be sometimes dangerous if you don't set constraints. The whole point I'm making here is writing or making fully autonomous programs. When it comes to machines that can harm humans, we had to be careful. We had to put very strict constraints on this, or there should be international conventions, international agreements prohibiting people from making anything or programming anything that can have full autonomy to hurt somebody, hurt a human being. So my point is, like, most often people focus on autonomous software programs, and they miss the point that there can be pure hardware programs like the landmine, which is functionally equivalent to a software code which is autonomous. So don't make the mistake in making. I'm talking to policymakers, very wise policymakers in the international bodies. Don't make the mistake of limiting your legal jargon to software codes. There can be pure hardware codes that can get away from these legal loopholes of if you draft it as only software codes. So anyway, so this is I just wanted to emphasize the damage it does to people if you have this kind of autonomous weapons, no matter how primitive they are. So this is Jaffna in Sri Lanka, and this is me, and these are my students who worked with me in my laboratory in Sri Lanka before I moved to the United States and then to London. We tried several ways of contributing some technology to improve the efficiency of landmine detection and removal. So then we went to these landmine fields to see how people are working, and then we saw how difficult it is. And then just to give you some kind of a clue, so this graph was shared by United Nations Development Program Office in Sri Lanka, Colombo. So these are accidents in Jaffna alone, and you can see these are females and the males, and then the highest number of accidents come from the male age group of 35 to 18 to 35. So this age group is the most productive age group, and then these are breadwinners, and then the male gets amputation. The female also has to bear the burden of raising a family, and then the whole family can get victimized in so many ways. So this is the catastrophe, the human catastrophe of having very dangerous, autonomous, but stupid weapons lying around in the ground, waiting for somebody to step on. So that is the weak or the primitive end of autonomous weapons, and then we have other autonomous weapons like drones, and the drones can also get a target, but these are more sophisticated and advanced weapon or weapon platform basically. So we know that autonomous machines and weapons are dangerous if not programmed with care. And how about semi-autonomy? Like, so in drones, it has autonomy to fly, and then the decision to take action rests with a human. and then the human gets feedback from all the sensors, the vision, and all the sophisticated, very advanced sensors that sometimes a human being, a human soldier on the ground at that point may not see properly. So this drone may be able to see, but there is a huge risk or a window uh, of giving misleading information to the decision makers. So there have been reports where drones have dropped weapons, lethal weapons, or taken lethal action against civilians. And then apparently the remote controllers did not intend to kill civilians, according to their reports. Then what goes wrong here? If the drone is sophisticated, and if the drone has so much sophisticated advanced sensory systems, and a human is not intending to do any harm to a civilian, how can we kill civilians? Um, the problem with this kind of accidents is like, so in real war, like old war, like First World War, let's say even the Second World War, the enemy saw the other enemy, right? So like people saw, okay, so that somebody on the other side of the ridge shot me or shot my friend, and then you don't generalize the hatred too much because you saw who shot your friend. But when your brother or when your sister, when your navy dies, and then you don't see the enemy, what happens is these people spread or generalize the hatred across the whole West, and that includes us. That include us, maybe the engineers or the robotic scientists. So we have a responsibility to engage in this discussion. So, what is wrong, really? So, who is autonomous in a drone, right? So, the human is autonomous, we think, uh, because a human can take map sensory situations to actions autonomously without asking anybody. The drone is semi-autonomous, but still that can go wrong. So let's kind of look at briefly about our central nervous system. So let's say our finger pricks on something, touches a pin or something. The pain signal goes through to the spinal cord, and if the pain signal is too much, it doesn't tell the brain to take action. So it just latches onto a very short circuit, and then it sends a signal about within about 30 milliseconds. Like, so if you reach the brain, it takes about 120 milliseconds, and then coming down again 120 milliseconds, maybe processing about 50 to 100 milliseconds, depending on the circuitry involved. So it is too long to take action, to reduce damage from a like a painful thing like pricking on your finger on a sharp object. So the evolutionary solution to this is that we make a shortcut and then send a big command to the muscles to take away the hand. So did the conscious brain get involved in that? No, it is like conditioned throughout evolution. Okay, so this is not an optimal action because like, so you can hit somebody near you, but it is more important to reduce damage to the finger. So it looks like, so when you're pressed with urgent situations, your conscious brain may not be involved in your decision making process. It can be very reflex type decisions. So it can be when we are in fear, when we are in so much anger, when we feel a lot of pain. We cannot guarantee that we have full conscious control. So that questions the nature of autonomy in the brain. So we think we are in control, we are on top of everything. We are doing things with the proper training, but reflexes can overtake. So this is some of the work I have done in the past at the Research Academy lab at Johns Hopkins University when I was a postdoc. So this says like so the what we saw was so the eyes can be leading the hand when the hand is cut off from vision. So if you ask somebody to look at where your hand is uh, under an opaque screen and then ask him to move the hand, the eyes can be lagging the hand if the eyes use some kind of a delayed feedback signal. Uh, but if the eyes are taking an output of a predictor in the brain, the eyes can be leading the hand. So exactly what we saw was like so eyes are leading something like in the range of 100 to 150 milliseconds into the future. That means uh, uh, the predictors in the brain are involved in the control system of the brain. So these predictors are formed over throughout experiences. So meaning once you train a soldier or once you train somebody to operate something in a teleoperation scenario, how these forward models or whatever these things are, that is predicting situations and predicting the consequences of actions, interferes with how you control this remote object. So that training really matters. Right? So now I come to this big point of philosophy, because a lot of uh, defense community is now talking about mindfulness and meditation, and even U.S. Marines are doing some meditation training. So I have to be kind of cautioning. I'm a Buddhist, so I want to caution people about this a little bit, because there's a big difference between concentration and mindfulness. The Buddhist notion of mindfulness and just simple concentration. So if we don't do it properly, we may not be really getting the brain models or internal circuitry uh, to to work like a guard. Guard means a guard in a gate, um, like a guarding our thoughts that lead to action. Right? So in mindfulness, we didn't know any scientific evidence until recently, right? So the recent work done by some scientists show that if you do different kinds of meditation, vipassana meditation, taught in Buddhism, um, so this white is baseline, and green is choiceless awareness, and red is loving kindness meditation, and the blue is just concentration meditation. You can see in red, so the in the meditators, the connectivity is on. Basically, just don't forget about this lateral, uh, posterior in insula. So that is like so this area becomes active. So that area, when that area is active, it can basically see uh, the working of other brain areas. So you get some kind of a third eye or some kind of a independent awareness that sees other thoughts in your brain. So it is some kind of a self awareness. It is. I mean, we think we have self awareness, but it's kind of more than that. That is like awareness of your awareness of the thoughts, so you can build up compared to the control surface. And then the frontal areas of medial frontal cortex, so that is responsible for mind wandering. And then what happens in meditators, this free mind wandering, just random wandering, reduces over time. So it is not concentration. It is like a loving kindness is different from concentration, and then more bodily awareness is a different thing. So just after 11 hours of integrated body mind training, uh, enter your cingulate cortex. So this area see a significant. I mean, just after 11 hours of training, in this is more or less vipassana meditation where you just monitor or just keep watching how the body sensations and the bodily functions work. So, for example, you can keep focusing or watching on the breath, how the breath goes up and down, and then once the mind is settled down, you just watch how other bodily functions work, the heartbeats, or the diaphragms, the tissues change the tension or the tenseness, the softness changes, and then you get to feel how the blood flows in the body and all the pulsations and all these things, and then you get to see that things are really working autonomously. Blood flow, you don't have control. The heartbeat, you don't have control. The kidneys work on their own, running their own programs, fully closed loop programs, and then you get to see that there's really nothing called me and my thing and I can control anything. There's nothing I can control. So even the mind or the thoughts, for example, like, so you get to realize that um, I cannot stop my thinking process, because just thoughts come and go, and then if I have control over thinking, I should be able to stop thinking. I cannot stop thinking, it just thinks, meaning, so there's nothing called a person who thinks, so it is this autonomous process. So this level of autonomy, when you realize that my thoughts just think, I cannot change it, I cannot stop it, I just, thoughts come and go, it looks scary. Because if the thoughts are dangerous that come up in your mind, if it closes this loop by pushing you to take action on that, even a trained drone operator can do a dangerous thing. Very recently in German wings, a pilot, a co-pilot, suicided with 150 passengers on board. I mean, that person was not bad. It is just a thought came to his mind, and then he latched on to it, unfortunately, and then it kept on pushing him, and then till suiciding, and then these things happen. So uh, having a completely sophisticated robot is not going to solve our problem. It is, if it is controlled by a human being, this wandering nature of the mind comes in series with this robot, and then that becomes some kind of a, we call the stochastic process, or is some kind of a random process. There are so many random variables there. They can go out or cross over beyond dangerous zones, or from safe zones to dangerous zones. But this is the point I want to make. So when a human mind is put in series with a semi-autonomous robot, uh, the robot can be perfect, but the interaction can drive, because the robot is feeding you with information, right? So in a drone, the drone cameras and all these sensors are feeding you information, and then it goes into your mind, and the mind uses reflexes, all your training and all your thoughts, and then it is now connected to actions, and then actions go to the drone. So in between there can be so many things happening, and then if we see that these thought processes are very autonomous, and then they come and go without your knowledge, so we have to have some kind of a training to make boundaries for these thoughts. So in Buddhist meditation, what we try to achieve is to develop four corner points, or four the guarding agents, the guarding four gates. So that is called metta, karuna, mudita, and upekkha. So the metta is loving kindness you develop, and then the karuna is you develop the nature of compassion in your mind. Mudita is another nature of mind, a state of mind where you you become able to be happy when other people achieve their objectives or other people become successful. Rather than feeling jealous, you develop the counter to jealousy. That is like you feel happy when other people become happy, other people become successful. And upeka is something very difficult to develop, which advanced meditators develop. Upeka is a mind that allows you to do things without expecting any positive return. So that is like, so you help people and you never expect anything in return. So this is called unconditioned or unbounded, unconditioned love. So when you have upeka coupled with metta, karuna, and mudita, you can show metta, you can show karuna, you can show mudita without expecting anything in return. Even if people whom you loved, whom you helped, or whom became happy when they were successful, if they turn back and do something bad to you, you're totally okay with it. So because you didn't expect anything positive about it. So you are kind of like a rock, solid rock. Waves can hit you, and then you are not moving, and you still spread metta, karuna, and mudita. So that is what we try to develop in this kind of mind, in mindfulness, in Buddhist meditation. So if this is what the U.S. Marines and U.S. soldiers are practicing, this is great. So I just wanted to make the point that it is not just concentration that is involved. So to go a little deeper into that Buddhist philosophical point of autonomy in the mind, I'm taking little few examples from Samyutta Nikaya in the Paticcasamuppada and Vibhanga Sutra, and this is the dependent co-arising. So according to Buddhism, uh, when a sensory stimulus hits the mind through any of the sensory doors, that is like it can be coming from the skin, it can be coming from the eyes, the nose, the tongue, the ears, and even the thoughts from the own mind. So that is why in Buddhism there are 6 doors for sensory stimulus. The field of awareness warps. So it warps. For example, there's somebody, and then the mind creates a split. Like there's somebody, and I see somebody. So it's a duality. So it warps the awareness field, a pure awareness field, into a split awareness. Like that is called consciousness. And so this split over time gets kind of differentiated more clearly. So that man, and then an attitude. The attitude is with me, and then that man is over there. But this is happening in the same mind, and then we don't realize that. So, and then we don't realize that my stand is in my mind, and then that enemy is also in my mind. But we have a split, or some kind of a warping effect in the field of awareness. So this is called Vijnana in Buddhism. So V is coming from Vibhinna or Vichinna or split, and Jnana is awareness. So this is split awareness. Split awareness is called consciousness in English, or differentiated awareness. So this process of differentiation is called prapancha. Prapancha in mental proliferation. Prapancha is the word used by Buddha in Pali. So it's because we are bombarded by the sensory stimuli from so many sources, uh, we we get a flux of this me and that me and that me and that, and then this flux just always works like a beehive, like, so a bunch of baby of bees inside us, and then we don't realize that the perception of me and that is coming from this big thing, big phantom me created by this sensory stimulus. So we hold on to that as I, and this is me, and then I, is a big complex thing. So Buddha also said, so these intentions decide the which path it takes in the differentiation. So chetana, or intentions, are really important. So what I say is, like, so if you train somebody to operate something, that a machine that can have lethal force over somebody, we must train intentions, not situations to actions. So intentions can be trained by cultivating metta, karuna, mudita, upeka, or greed, hatred, and delusion will be kind of suppressed by these things. So my concluding remarks: so there's a need for multidisciplinary effort to bring in regulatory guidelines for autonomous robot-human coexistence interactions. And then the focus should be on both the autonomy of the robot and that of the humans. And the failure will delay productive growth in autonomous robots that can do very good things in the society. For example, good autonomous robots that can be a proxy to a disabled person, and the disabled person owns this robot, and maybe take a bank loan and then mortgage this robot, and the robot works in a factory and earns money for this disabled person. So that's the kind of future I'm envisioning. These are the good folks, brilliant people in my lab who are working day and night to advance science in this field. So these are PhD students and postdocs. So thank you to them. Thank you very much.